Hi, and welcome back to another video. So in today's video, we're going to be exploring differential equations a little bit. In particular, for this video, as well as the next few videos, we're going to be looking at second-order differential equations and various forms of second-order differential equations. In particular, today we'll be looking at second-order constant coefficient differential equations, which is a mouthful, but the name kind of implies what it is. So today we'll be talking about that, discussing how to solve these problems, and in future videos we'll see variants of second-order differential equations. So let's get into it. Here we see the general form of a second-order differential equation. Typically, differential equations are equations which involve some sort of function and its derivative. So most commonly we use the variable y, where y is going to be some function of x, and then we have derivatives of y also in the equation. So we have y, y prime, and y double prime. Of course, with equations we also have coefficients to our variables. So in this case, our coefficients are denoted with a of x, b of x, and c of x, where these can be functions of x. Today we're talking about constant coefficient differential equations, which means for today, a of x, b of x, and c of x will all be constant values. They will not be functions of x. They'll be numbers like 2, 5, etc., etc. And in fact, right here, we see an example of what a constant coefficient differential equation will look like. We have y double prime minus 2y prime minus 3y equals 0. And you can start to make connections where a of x is equal to 1, b of x is equal to negative 2, c of x is equal to negative 3. Sure enough, those are all constant values, so we have a constant coefficient differential equation. Before we learn how to solve these differential equations, I'm actually going to give the solution for this differential equation, and we'll just check to see that we understand that, yes, that is the solution. So the solution to this differential equation is y equals c1 e to the negative x plus c2 e to the 3x. And c1 and c2 are just constant values in this expression right here. In fact, they're any constant. I can choose any value of c1 and c2, and as long as it's some sort of constant, this will be a solution to that differential equation. So now let's check to make sure that I didn't lie and this solution is actually correct. And this is how you would go about checking your solutions when you learn how to solve these differential equations. And we'll get into solving it very shortly. But first, I like to go about checking it. So we have y already here. We would like to find y prime and y double prime. Then we'll substitute and hope that it equals 0. So to get y prime, we'll take the derivative of this equation with respect to x. And we see that this will be c1, and then you take the derivative of this, which will require the chain rule. So it's going to be c1 times negative e to the negative x. And then we add on to the c2, and once again the chain rule, which is times 3e to the 3x. And I'll just rewrite it so it looks a little bit better. This is negative c1 e to the negative x plus 3c2 e to the 3x. And then we need y double prime. So we can take the derivative of this with respect to x, and we should get c1 e to the negative x plus 9 c2 e to the 3x. Cool, so now we have these three, and we're just going to substitute into here, into the left-hand side, and hope that it equals 0. So let's do that over here. So y double prime is c1 e to the negative x plus 9 c2 e to the 3x. We're subtracting 2 times negative c1 e to the negative x plus 3 c2 e to the 3x. And then we're subtracting 3 times y, which is c1 e to the negative x plus c2 e to the 3x. All right, so now it's just a little bit of algebra. So we'll just drop the parentheses wherever possible. So the first two terms stay as is. Then minus 2 times minus 1 becomes plus 2 c1 e to the negative x minus 6 c2 e to the 3x. Then distribute this minus 3, minus 3c1 e to the negative x minus 3c2 e to the 3x. Now it's just about grouping like terms. So this is a c1 e to the negative x. This is c1 e to the negative x. And this is as well 1 plus 2 minus 3 is equal to 0. So it's like 0 c1 e to the negative x plus, we have 9 c2 e to the 3x minus 6 c2 e to the 3x gives 3 c2 e to the 3x. Minus 3 is 0 c2 e to the 3x. And this is just equal to 0. So our solution is correct. And that's how we go about checking these second order, constant coefficient second order differential equations, which is a lot of words. No, actually I want this. Okay, so let's see one more example differential equation before we learn how to solve it. Y double prime plus 11 halves y prime minus 3y equals 0. And again, this is a second order constant coefficient differential equation. It's a differential equation because we have an equation of y and its derivatives. It's second order because it goes up to the second derivative, and the coefficients 1, 11 halves, and negative 3, they're all constant. I'll give you the solution to this differential equation. So the solution is y equals c1 e to the 1/2 x plus c2 e to the negative 6x. And so the reason I'm showing you these examples and these solutions before we even learn how to solve these is to hopefully gain some insight into what these solutions are. What do they look like? Are there any patterns we detect? And we should be able to get one pattern right off the bat. And you'll see that I boxed this solution up here, which was the solution for our first example. And I'll box this down here, which is the solution to our second sample differential equation, and hopefully we're starting to see some patterns. Both of them have two terms in our solution. Both of them have the C1 and C2, but this is going to be a motif that we see throughout solutions to differential equations, where we have some sort of fundamental solution, and any linear combination of it, meaning any sort of sum of the multiples of our solutions, will give us a different solution. If that doesn't make sense, don't worry too much. But yeah, the C1 and C2 are common, but the actual terms are very similar. They're both e to some power with an x term in there. E to some power with an x term in there. Is that a coincidence, or is that just a good pattern that we've noticed? Well, it's actually a pattern. It's not just a coincidence. So now let's learn how to solve these. Okay, so here is the game plan to solving these constant coefficient second order differential equations, which is becoming increasingly more annoying to say by the minute. Oh well. Our first step is we're going to guess our solution. And this, to me, is one of the most unsettling motifs of differential equations, where oftentimes to solve them, we guess an answer and hope that it's correct. But notice what we're guessing. We're going to guess that our solution is y equals e to some power of x. And this is why I showed you these examples in the beginning. Both of these have solutions of the form e to some power of x. So we're just going to say, hey, that is our solution. I don't know what this value of k is, but I'm going to solve it because I'm pretty darn sure my answer is going to be e to some power of x. So we're going to guess that as our solution, and we're going to substitute it into our equation, of course by taking the derivative of y and the second derivative. From there, we're going to be able to factor out an e to the kx term. And the short explanation for this is when you take the derivative of y equals e to the kx, the nice thing about exponentials is that the exponential term stays. It's preserved when taking the derivative. Sure, there's going to be some sort of factor out in front of it, but the actual exponential term itself is preserved. And you might note that, oh, if k is a constant, then it's going to be a constant times that when I take the second derivative. And that works nicely because all of my coefficients are constant. But that might be a little bit too much. From there, we are going to solve something called the auxiliary polynomial. Fun fact, this word I can barely pronounce it. I remember in school we used to have something called the auxiliary gym, and I could never say that. So I would just call it the aux gym, but I would like auxiliary polynomial. What is that? We'll see it in a moment by going through an example. But we're going to be able to obtain some sort of polynomial in terms of k, and we're going to solve it, meaning we're going to find the roots of it. And we'll use the roots of the aux poly to construct our answer e to the kx. So we'll basically say, yes, our guess was correct. Here are the values of k that work. And so the best way to understand this procedure is by actually doing an example. So here we see an example, y double prime minus 2y prime minus 3y equals 0. This should be feeling very familiar because that's right up there. But now we're actually going to solve it. So we'll follow the game plan. The first step is to guess our solution. So we're just going to say, let y equal e to the kx. And we're going to try to figure out what is this mysterious value of k by substituting into here. Well, let's find y prime and y double prime. So then y prime is going to equal k e to the kx. And y double prime is k squared e to the kx. From here, we can substitute back into our original differential equation. So y double prime is equal to k squared e to the kx minus 2 times y prime. So this is minus 2k e to the kx. And minus 3 times y. So this is minus 3 e to the kx. And we're saying that equals 0. Step 2 says to factor out the e to the kx term. And indeed, e to the kx is present in all three terms, so we can factor it out. And that comes from, like I mentioned before, the preservation of exponentials when taking the derivative of exponentials. So this means e to the kx times the quantity k squared minus 2k minus 3 equals 0. Well, we can argue that that means either e to the kx equals 0 or this polynomial equals 0. Well, we should know from functions of these exponentials e to the kx that this is never equal to 0. So in fact, e to the kx will never be 0. That must mean that it's k squared minus 2k minus 3 that's equal to 0. And this is what we call the auxiliary polynomial. And since that's equal to 0, it makes sense why our third point is to solve the auxiliary polynomial for k. I'm just now realizing that this looks like the word fork. Anyways, let's solve this auxiliary polynomial. K squared minus 2k minus 3 equals 0. We can factor this into k minus 3 times k plus 1, which means k equals 3 or k equals negative 1. Now remember, we said that our solution is going to be y equals e to the kx. And now we've found our values of k. So that means y equals e to the 3x is a solution to the differential equation, and y equals e to the negative x is also a solution to this differential equation. But what we do here is we take our two solutions and we take a linear combination of them. Basically, one can argue if this is a solution to our differential equation, and this is also a solution, then their sum must also be a solution to the differential equation. And similarly, any constant multiple of these will also be solutions to the differential equation. So our final solution is going to be y equals c1 e to the 3x plus c2 e to the negative x. We're taking a linear combination which means we're considering all multiples of our solutions, rather any multiple of our solutions, as well as the sum of any multiples of our solutions. And no matter what value of C1 and C2 you choose, that's going to be a solution to our differential equation here. And we see that that matches our solution up there. I just swapped the two terms. So why does this work? Why does this game plan work? Let's think about it here. When we're faced with a second-order constant coefficient differential equation like this, where it's homogeneous, or some might say homogeneous, meaning that it's equal to 0, we're looking for a solution such that when we plug it in and then take its derivatives, we have three terms that will eventually cancel out, leave 0. And we know that y is going to be some function of x. So in essence, we're really looking for something in which y double prime, y prime, and y are all like terms. They have to be like terms because the only other thing influencing the terms is the constant coefficients. And since they're constant coefficients, for them to be like terms, they will still remain like terms after multiplying by constant coefficients. Imagine if this was an x here instead of a 2. Then I don't need y prime and y to be like terms in order for this to cancel, because I have a function of x being multiplied with y prime. Since this is just a constant, we need all of these derivatives to be like terms. That's why we chose the exponential function, because when we take the derivative, it'll preserve the likeness of terms within the derivatives. So a keen observer might have realized that this seems to work really well when the solution to our auxiliary polynomial has distinct real solutions, right? Here we have two solutions, 3 and -1. They're different and they're real. Here you can start to guess that, oh, there was probably some sort of auxiliary polynomial, and its solutions were probably 1/2 and -6. Again, distinct real value solutions. What happens when that's not the case? For example, what happens when the solutions are not distinct? We can have auxiliary polynomials where the roots have multiplicity greater than 1. Or what happens when there's imaginary roots? That's what we'll look at next. Okay, so a couple of things have changed. First of all, I erased all of the boards. I rewrote the game plan here in less words. And the second thing to note is I added the word homogeneous here in parentheses. We're still talking about these second-order constant coefficient differential equations, but the main thing to note is that right now they're just homogeneous differential equations, meaning the right-hand side is equal to 0. We'll see in future videos differential equations that are non-homogeneous, where we have some other value on the right-hand side, whether that be some sort of constant or a function of x. But for now, we'll just concern ourselves with homogeneous differential equations. And another thing is we have another problem right here. So we're going to solve this basically the same way we did the previous problem. So we'll follow our game plan. So the first thing we'll do is we'll guess our solution, which is y equals e to the kx. And we're going to solve for our value of k. Let's find the first derivative of y. So y prime is equal to k e to the kx. And y double prime is equal to k squared e to the kx. From here, we'll substitute back in. So we get k squared e to the kx plus 6k e to the kx plus 13 e to the kx equals 0. My k's are very funky. They vary in styles, but they all mean the same thing. Cool. So the next step of the game plan says to factor out an e to the kx, which works nicely since we have an e to the kx in all three terms. So this is e to the kx times k squared plus 6k plus 13, and we say that that's equal to 0. Well, that means one of these two things is 0. We know the exponential can't be equal to 0, so it must be the polynomial that's equal to 0. So let's find what values of k make that equal to 0. In our previous problem, we just factored our auxiliary polynomial and then just looked at it and said, hey, these are our solutions. And that worked really nicely. But now our polynomial is not easily factorable. But still, we can find the values of k that make this equal to 0 by using the quadratic equation. So let's see. Negative b, negative 6, plus or minus the square root of b squared, 36, minus 4ac, so 4 times 1 times 13 is 52, all over 2a, which is 2 times 1. So that's 2. Okay, so this is equal to negative 6 plus or minus. This becomes the square root of negative 16. But that's equal to the square root of 16 times the square root of negative 1. And the square root of 16 is equal to 4. The square root of negative 1 is equal to I. And we're dividing by 2. Which tells us that k is equal to negative 3 plus or minus 2i. Cool, so like our solution would say that we should write y equals c1e to the choose your favorite root, negative 3 plus 2ix, plus c2e to the negative 3 minus 2ix, right? Where we take our two solutions for k, put them back into our guess, e to the kx, and then take a linear combination of it. The thing is, right now, our solution is imaginary. It has these I terms in it. But we're only looking for real value solutions. So how can we make sure that we have only real value solutions? Ta-da! Well, that's where Euler's formula comes into play. So Euler's formula tells us that e to the ix can be rewritten as cosine of x plus I sine of x. And while this still has an imaginary term in it, we can easily handle that later. So let's apply Euler's formula to our solutions. Well, let's consider e to the negative 3 plus 2ix. That can be rewritten as e to the negative 3x plus 2ix, or equivalently e to the negative 3x times e to the 2ix. So now we can use Euler's formula on this 2ix. We don't really care about this negative 3x because that's still a real part. So that's going to be equal to e to the negative 3x. And then here, we just have to be careful with how we're doing this. So we'll think about x as 2x instead of just normal x. So this will be cosine of 2x plus I sine of 2x. And you can do the same thing for the other solution. So e to the negative 3 minus 2ix is going to be equal to e to the negative 3x times cosine of negative 2x plus I sine of negative 2x. And so now when we reconsider our solution c1 times e to that and c2 e to that, we can rewrite it in terms of this. So we would have like y equals c1 e to the negative 3x times cosine of 2x plus I sine of 2x plus c2 e to the negative 3x times cosine of negative 2x plus I sine negative 2x. And in fact, we can reduce this down quite a bit. We'll utilize the fact that cosine is an even function. So I'll write that here. Cosine is even, which means that cosine of negative x equals cosine of x, and sine is odd, meaning that sine of negative x is equal to negative sine of x. And the reason I'm doing that is because I want these to be like terms, and I want these to be like terms. So we have y equals c1 e to the negative 3x times cosine of 2x plus I sine 2x, and then c2 e to the negative 3x. But now we'll use evenness to say that this is equal to cosine of 2x, and then we're subtracting now an I sine of 2x. From here you can group like terms and say that this is equal to something like c1 plus c2 e to the negative 3x cosine of 2x plus I times c1 minus c2 e to the negative 3x sine of 2x. But there's a couple of things we can do here. Remember, c1 and c2 are just constants. We don't really care what they are, so I don't really care that they're being added together because that'll just be a constant. So I'll just say that this is some constant c1, and similarly this difference is some other constant c2. And we're so close. We still have an imaginary part to our solution. Ready for this? We can remove it altogether. And this is our answer. Why did we remove it? There's a couple of explanations for this. The simple explanation is that our solution is a linear solution, which means we can take any sort of linear combination of it and get another solution, which also means we can divide by any constant value and get a solution. So we had an I here. If we divide this by I, this will also be a solution. And we let c1 and c2 be real, and now we're only considering real value solutions. So we're just able to drop that I altogether. Let's see one more example. The reason for that is I only had one more example planned, but the second reason is my laptop's on 5% battery. I'm kind of stressed. Okay, last example. We do it the same way. First, we'll guess y equals e to the kx. We have y prime equals k e to the kx, and y double prime equals k squared e to the kx. Let's substitute. K squared e to the kx plus 4k e to the kx plus 4 e to the kx equals 0. Factor out our e to the kx. We know that our auxiliary polynomial must be equal to 0. So we have this is equal to 0. This is nicely factorable into k plus 2 times k plus 2. So that means k equals negative 2. That's our only root. So does this mean that our solution, like normally we would write c1 e to the negative 2x plus c2 e to like some other value of kx, but since we don't have another one, is this our solution? Not quite. When we have a root of multiplicity 2, we still add in another term. It's nearly identical, the constant and the same exponent, but we multiply it with x. We're not going to delve into the reasoning behind this, but it's important to note when you have a root of multiplicity 2, you add in this extra factor with x there. We're running on 2% battery now. These are our findings summarized. What you can do is basically just look at your auxiliary polynomial. And in particular, look at the discriminant, which is b squared minus 4ac. If the discriminant is greater than 0, that means you're going to have two distinct real value solutions, which means if your roots are r1 and r2, this is going to be your solution for the differential equation. If the discriminant is less than 0, you're going to have two distinct imaginary solutions, written a1 plus b1i and a2 plus b2i. Then your solution is that. You can just plug in your values there, and that can be a good way of checking your work. Like, this is your answer. And if it's equal to 0, then you have one root with multiplicity 2. That's your solution. So it's all of the work summarized into this. You just need to look at your discriminant of the auxiliary polynomial and substitute your values into here. As simple as that. I hope you enjoyed. We'll explore some more differential equations in the future. But for now, this is constant coefficient differential equations for second order differential equations, homogeneous. We'll explore more in the future. As always, take care and see you next time.